Hello, I am Ms. Prabhavati SN. In today's module, I will be talking to you about the major factors accelerating the losses of water soluble vitamins and the factors affecting its bioavailability. Vitamins are essential for health and have to be obtained from diet on a regular basis, with the exception of vitamin D, since it can be obtained from sunlight. A number of substances were designated as vitamins in the early 1930s and 1950s. But as per the knowledge of nutritional sciences, only 13 substances have been recognized as true vitamins. These 13 substances have been divided into two categories as fat soluble and water soluble vitamins. The fat soluble vitamins have a definite storage sites in the body and can be stored for a considerable period of time. Fat soluble vitamins are quite stable to environment as well as processing conditions in comparison to water soluble vitamins, which are highly susceptible to degradation under storage as well as during preparation by as much as 50%. This could be due to its chemical nature. Highly reactive nature of food components with the available factors could bring about significant amount of losses. Certain vitamins also possess subcategories within the given group but appear to have no common attributes with respect to chemistry, function or the daily requirements. Since water soluble vitamins have a greater tendency to undergo rapid degradation, it becomes necessary to understand the factors which accelerates the rate of destruction and the various measures that can be adopted to minimize the vitamin losses. After studying this module, you would be able to define the factors affecting the stability of vitamins, determine the conditions promoting the loss of water soluble vitamins, and understand the factors associated with the bioavailability. Now let us study the major factors affecting the stability of vitamins. None of the vitamins in the food are completely stable and is the common attribute which is generally observed in case of all vitamins. The stability of individual vitamins tends to vary from one to another, from being relatively stable in case of niacin to a highly unstable nature of vitamin B12. The factors that are known to affect the stability is being reported to vary from vitamin to vitamin. The most important factors promoting degradation are heat, moisture, oxygen, pH, and the light. Deterioration has been said to take place naturally during the processing and preparation of foods, and accelerated losses might occur when they are subjected to heat treatment. The factors that are known to affect the degradation of vitamins, irrespective of whether they are natural or from synthetic sources, is known to be associated with similar factors that promote degradation. For instance, in packaged goods, the shelf life of a product is generally determined by the life of the most unstable compound in a given food matrix. Let us now discuss the factors affecting the stability of individual vitamins in detail. The first vitamin is thiamine. Several investigations have been conducted with respect to the stability of thiamine and its salts in the context of cooking losses. Early work in this area has pointed that the destruction to be more rapid in alkaline media. The thiamine content of fresh milk is 0.04 mg per 100 ml. In case of pasteurized milk, it may be less than 10% of the reported value. 5 to 15% losses can occur in UHT milk, and 30 to 40% reduction might occur in sterilized milk. About 30 to 50% losses have been recorded during the production of evaporated milk. Commercial baking of white bread results in 15 to 20% losses. This loss is partly attributed to yeast fermentation, which converts thiamine to co-carboxylase, which is relatively less stable than thiamine. Thiamine is relatively unstable in alkaline solution, and degradation tends to increase with increase in pH. It is relatively stable in fortified fruit drinks with a low pH. Riboflavin. Light is the only single factor that is known to affect the stability of this vitamin, and greatest effects are said to occur by light in 420 to 560 nanometer range. Fluorescent light is considered to be less harmful than that of direct sunlight. Products that are packed in transparent packages could be affected by strip lighting in retail outlets. Riboflavin as well as riboflavin phosphate exerts maximum stability to heat atmospheric oxygen, in particular in an acid containing medium. With respect to this particular aspect, riboflavin is regarded as one of the most stable vitamins. It is known to be degraded in the presence of reducing agents. pH also exerts impact on its stability. With increase in the pH level, it makes the vitamin highly unstable. Though riboflavin is stable, during the heat processing of milk, losses are expected to occur when milk and milk products are exposed to light. When liquid milk is exposed to light, about 20 to 80% of the vitamin might be lost in 2 hours. The rate and extent of loss is reported to be highly dependent on the intensity of light, temperature, and the degree of loss is generally dependent on the container that is exposed. Niacin. Niacin is a generic term used to refer to both nicotinic acid and nicotinamide found in foods. Both forms exhibit same vitamin activity and are available as commercial isolates. It is naturally present in meat, liver, as well as in some plant species. In maize and cereals, it is present as niacin, which is the bound form and is reported to be unavailable. Mild alkali treatment improves the bioavailability. Both forms of niacin are considered to be highly stable to atmospheric oxygen, heat and light in both aqueous as well as solid food systems. Pantothenic acid. Losses occurring during cooking and preparation are reported to be very minimal. In case of milk processing, the estimated losses are about 10%. Losses during the cooking of meat are reported to be not excessive. Free pantothenic acid is highly unstable and very hygroscopic in nature. Commercially, it is available as calcium or sodium salts. D-panthenol is an alcoholic form which is quite stable but not generally used in food processing. Calcium and sodium D-pantothenate and D-panthenol are moderately stable to oxygen and light in the absence of moisture. All the forms are highly hygroscopic. In aqueous preparations, both the salts and its alcoholic forms are thermolabile and it undergoes hydrolytic cleavage, particularly at high or low pH containing environments. The compound is known to degrade under acid and alkaline medium. Maximum stability has been reported at a pH range of 6 to 7. D-panthenol, when used as an aqueous solution, is being reported to be more stable than its salt form, provided the pH range is between 3 to 5. The next vitamin is folic acid. Folic acid or the terroyl glutamic acid does not exist in nature but can be manufactured commercially. The naturally occurring compounds are basically the derivatives and are collectively termed as folates or folacin, which may contain one or more molecules of glutamic acid. Polyglutamates are predominantly found in fresh foods, but upon storage they tend to break down slowly to monoglutamates and would get oxidized to folates that are biologically less available. Most of the stability studies have been performed using commercially available folic acid, which is known to exert moderate stability to heat and atmospheric oxygen. At a pH level of 7, it is relatively stable and may become unstable in an acid or alkaline media, particularly when the pH is less than 5. It decomposes rapidly by oxidizing and reducing agents. Sunlight and UV radiation causes deleterious effect. When milk is subjected to pasteurization, the estimated losses were found to be less than 5%. Losses can be as high as 20% in ultra-high temperature treatment, and sterilization processes would increase the losses up to 30%. UHT milk that has been stored for 3 months was reported to have lost 50% of folate. Vitamin B6 or pyridoxine. The compounds such as pyridoxal, pyridoxal and pyridoxamine are known to possess vitamin B6 activity. These are collectively known as pyridoxine. It is found in red meat, liver, milk and green vegetables. It is generally considered as a relatively stable compound to oxygen and to heat. Decomposition is known to be catalyzed by metal ions. It is highly sensitive to light in neutral and alkaline solution. Losses in milk can occur through the exposure to sunlight. About 21% of vitamin was reported to be lost after 8 hours of exposure to sunlight. Pasteurization of milk is not been reported to cause any losses, but sterilization can result in 20% loss. UHT processing leads to 27% loss, and further higher losses are known to take place in stewed and boiled meat in the range of 30 to 60%. Cooking or canning of vegetables could result in 20 to 40% loss. Vitamin B12 or cyanocobalamine. It decomposes readily in the presence of oxidizing and reducing agents. It is reported to be relatively stable to oxygen and heat in neutral and weakly acidic solution. Under alkaline and strong acidic conditions, it is only slightly stable. It is highly sensitive to light and UV radiation. A brightness of 8,000 food candles can bring about 10% losses for every 30 minutes exposure. It is generally stable under pasteurization. Sterilization leads to 20% of loss. Spray drying generally leads to slightly higher levels of losses amounting to 20 to 35%. Its stability is known to be strongly influenced by the presence of other vitamins. Biotin. Of the 8 different isomers, only the dextrorotator or D-biotin possesses vitamin activity. D-biotin is widely distributed but is present only in small concentrations in both animal and plant tissues. In milk, fruits and vegetables, it occurs in free state. Whereas in animal tissues and yeast, it is present in bound form with protein. The commercial form is available as a white crystalline powder. It is generally been considered to have good stability. It is fairly stable in air, heat and dry light. Gradual decomposition is expected to occur in the presence of UV radiation. Vitamin C or ascorbic acid. Many compounds are known to possess vitamin C activity, among which the most important is L-ascorbic acid. It is widely distributed in nature and may be present at relatively high concentration in certain fresh fruits and vegetables. It is also found in animal organs such as liver and kidney. The L-ascorbic acid is readily prone to oxidation and would be converted into dehydro-L-ascorbic acid. The reduced form of vitamin is predominantly found in fresh foods, but processing, storage and cooking tends to increase the proportion of the dehydro form. Ascorbic acid is readily oxidized in aqueous solution. The stability of ascorbic acid in soft drinks is said to be highly variable and is known to be highly dependent on the composition and oxygen content of the solution. About 1 mg oxygen can destroy 11.2 mg of ascorbic acid. Traces of heavy metal ions would tend to act as catalysts and may result in the degradation of ascorbic acid. About 0.85 ppm copper ion would catalyze the oxidation process. The degradation of ascorbic acid in aqueous solution is reported to be pH dependent. About 10% loss has been reported to occur in frozen storage. Contact of ascorbic acid containing food product with bronze, brass or black iron surfaces accelerates the losses. The stability of vitamin C in milk is known to be affected either from sunlight or white fluorescent light. Pasteurization losses would be about 25%, sterilization 60% and 100% in case of UHT milk that was stored for 3 months. Huge amount of losses are reported to occur after cooking or hot storage of vegetables and fruits. The losses in commercial dehydration of potatoes would be 35 and 45% respectively. Other means of losses can occur through slicing and dicing. Blanching of cabbage causes 20% of destruction. A subsequent dehydration process amounts to 30% of loss. Moving on to the second part, that is the bioavailability of the above discussed vitamins. It can be defined as a process in which fraction of an ingested nutrient which may have the potential to meet the demands in target tissues. So far, bioavailability has been usually assessed by measuring the amount of an ingested oral dose which in turn enters the circulating plasma. For instance, it can be evaluated by monitoring the post-ingestion area under the curve. This approach has been known to yield useful results, but it has been reported that in many cases it is likely that the obtained results may be inaccurate. This could happen due to nutrient utilization with the circulatory system, its movement from plasma into intravascular spaces, cellular uptake and renal losses, and leakage or release from cells. These processes could result in a gross misinterpretation of the bioavailability status. Now let us discuss the bioavailability factors of the individual vitamins. Thiamine. Several food products are known to contain anti-thiamine factors which results in the inactivation of thiamine. Heat labile enzymes are generally found in raw or fermented fish, shellfish and some bacteria. These foods when consumed in raw form are known to have anti-thiamine activity. Heat stable thiamine antagonists are also found in several plants such as ferns, tea and betel nut. These are known to have higher concentrations of tannins, a major component that can yield non-absorbable thiamine disulfide. In order to increase the bioavailability, it is recommended to delay the consumption of tannin containing food products after a meal. Riboflavin. Only a small amount of riboflavin is being estimated to present in foods as free riboflavin. Flavins that are present as covalent bonds with enzymes are reported to be not available for absorption. During absorption, both flavin adenine dinucleotide and flavin mononucleotide should be hydrolyzed to riboflavin before being absorbed and is the most prerequisite condition needed. Information pertaining to bioavailability from different food sources is very scarce. Niacin. Bioavailability of niacin from unfortified foods is reported to be often very low. Significant proportions generally exist in bound form that will not be absorbed by humans or cannot be utilized even though they are absorbed. Grains that are consumed without pre-processing would make the vitamin unavailable. Bioavailability from wheat and wheat products can be as low as 50%. Studies have demonstrated that protein-bound nicotinic acid and glucose esters are reported to be partially available to humans. Pyridoxine. The bound forms of pyridoxine are generally known to affect the bioavailability. Animal products have been estimated to contain higher levels of bioavailable forms of pyridoxine in comparison to plant sources. In plant-based foods, pyridoxine exists as a beta-glucoside whose level seems to be quite variable in plant products and almost absent in animal products. In products such as broccoli, cauliflower, carrots and cooked soybeans, more than 50% of pyridoxine would be present in the form of pyridoxine glucoside. Pyridoxine glucoside is also present in potatoes and the content is known to increase during storage. Bioavailability studies on pyridoxine glucoside have shown that the compound is poorly absorbed in both humans and animals. Folate. The hydrolysis step is known to play a significant role in the absorption of folates. The polyglutamates through a hydrolysis step are converted into monoglutamyl folates in the brush border of the intestine. Bioavailability from milk is said to be quite satisfactory since it is known to contain folate binding protein which would help to increase the folate absorption via inhibiting dietary folate uptake from the bacteria in the gut. Extrinsic factors such as chemical form of the vitamin, its concentration, physical form and composition of diet, and intrinsic factors like age of an individual, health status, impaired digestive function and poor nutritional status are known to impair the rate of bioavailability. Dietary interactions, mainly the intestinal pH, presence of folate antagonists, intestinal changes occurring through alcoholism are known to exert significant effect on the overall bioavailability. Vitamin B12. Certain foods are known to contain vitamin B12 binding protein which tends to resist the digestive process and thus would affect the uptake by the intrinsic factor. Elderly individuals generally have reduced secretion of gastric enzymes which tends to accelerate the effect of food origin vitamin B12 binders. Raw egg yolk and albumin are known to have specific vitamin B12 binding proteins. These binders could be very effectively inactivated by subjecting the foods to heating. Mutton, chicken, fish, milk and fortified bread do not contain apparent vitamin B12 binding capacity. Pantothenic acid. Urinary assays provide objective information on the bioavailability. Excretion is dose dependent and a parabolic increase in excretion rate occurs when intakes are between 0 and 10 mg per day. Bioavailability has been reported to be largely dependent on the hydrolysis of CoA and phosphopantothene to form pantothenic acid by the enzyme pantothenase in the intestinal lumen prior to absorption in the jejunum. Vitamin C. In order to promote the oral absorption efficiency, it is suggested to ingest it in a smaller dose rather than consuming a single large dose. The major site for vitamin C absorption is small intestine. Hence, delayed gastric emptying could promote its retention and thus would enhance the rate of bioavailability. Let us summarize today's episode. Vitamins are essential for health and have to be obtained from diet on a regular basis with the exception of vitamin D since it can be obtained from sunlight. None of the vitamins in the foods are completely stable and is the common attribute which is generally observed in case of all vitamins. The stability of individual vitamins tends to vary from one to another, from being relatively stable in case of niacin to a highly unstable nature of vitamin B12. Deterioration has been said to take place naturally during the processing and preparation of foods, and accelerated losses might occur when they are subjected to heat treatment. Bioavailability encompasses the major processes such as ingestion, absorption, distribution, utilization and loss. To have optimal absorption efficiency, it is recommended to avoid the intake of certain foods that are known to have antagonistic property.